Hello, everyone, and welcome back to our online lessons. Today we will be talking about geometry, just like we were before Easter break. So today we're going to focus on theory, and tomorrow we are going to do some more exercises together, some problems, some examples. Specifically, today we're going to talk about symmetry, how to define triangles based on their sides instead of their angles, which is what we were talking about before Easter, and how to draw the height of a triangle. We'll start simple with symmetry, which is something that we have talked about before in the past, but because it is very important, we are going to need to remember how it works. So, symmetry. Asking if a shape is symmetrical is basically like saying, could I draw a line for this object? So let's draw a line here, where if I were able to fold that object on that line, one half would fall exactly on the other half. It's basically like they're mirror images of each other. Like imagine there's a mirror right here in the middle between them. Well, this is what one side of the mirror would show. So if that is true, then indeed this is what we call a line of symmetry for this shape, for this object, let's say. So let's see if this works. Let's see if this is indeed a line of symmetry. Let's see. If it is, then what should happen is that if I make this half blue, and then I were to fold it onto the gray half, then the blue half would fall exactly on the gray half. Let's see if that's going to happen. This might not be exactly 100%, but it should. Sorry about that. It should be almost 100%. And as you can see, yes, the gray part hides the blue part perfectly. And if I take away the gray part, there's the blue part, right? One falls on the other exactly like it is supposed to. Okay, so what can we do with this information? We could be asked, well, where are all the lines of symmetry of this star, for example? Well, here we already drew one, that was here, and all of the lines going from the head of each star, each point of the star, to uh, this angle right here, and I'm trying to get it exactly, but it is not working. So let's say like this. Oh, that was too much. Like that. And then let's say here. This is approximately, it's not exactly. All of these are lines of symmetry, as you can see. And I can bring another one here. That's not exactly on the point, although it should be. And another one here. Yeah, that's too far away. There we go, that's exact. And that last one, let's fix it actually. So all of these are lines of symmetry for the star. If I were to fold the star on any of these lines, one half of the star would fall on the other half exactly. Okay, but what if I were to claim that this is a line of symmetry? What if I fold this top half on this bottom half? Well, then no. The top half, as you can see, is more than the bottom half. And if you want to see that with more detail, we can make a copy of the blue star, make it black, and then turn it around. Just a second. Turn it on its head. So its head would need to be here. What you'd get basically is something along these lines. This half, let's say that this half was folded. What you would see is something like this. And as you can see, the black half, the top half, did not fall exactly on the blue half. There's still some left. There's some left over from the blue. And the black has all these angles just going out everywhere. So, and you can even see that a little better actually. If we make this black half a little more transparent, you can see that it does not, as a matter of fact, fall on the bottom half exactly. So that line that I made was not a line of symmetry. This line right here is not a line of symmetry. So we can't just draw any line we want. We can't just say, okay, well, here's a line, there's a line, and there's a line, and there's a line. We can't just draw any line we want and say, okay, there's a line of symmetry just because it cuts the shape. No, we have to think carefully. If I fold the shape on this line, will one half fall exactly on the other half? That's a bit more difficult than it sounds, especially with more complicated shapes. Okay, so there goes symmetry. We'll focus more on that tomorrow. Next, we're going to be talking about triangles and how we define them based on their sides. We talked about, before Easter, we talked about how we define triangles based on their angles. So there was, for example, the right angle, the right triangle, the obtuse triangle, and the acute triangle. We talked about all these types of triangles, but all of them had to do with what kind of angles the triangle had. We never talked about its sides. We didn't really care what was happening with the sides. Well, now we're going to talk about how we refer to triangles based on their sides. So first things first, the basically the one that has nothing particular about it is the one that has no real defining characteristic. One side has nothing to do with the other. They're all different. And it doesn't have to be obtuse like I made it here. It can be acute as well. So here you go. Here's an acute, uh, yeah, here's an acute triangle where the sides are all different. Well, these two sides seem kind of the same. So let's try that again. Here you can see I've made an acute triangle where none of the sides are the same. None of them are equal. None of them have anything to do with the other. We call these types of triangles where all the sides are different. We call them scalene triangles. In scalene triangles, all the sides are different. Okay, but what happens if two sides are the same? So let's imagine a triangle like that. I have this side here, and then I have this side here, and they look pretty much the same, don't they? And it doesn't have to be acute like it is here. It could be obtuse. Look at that. I'll make one here. So this angle right here is obtuse, whereas this one is acute. And again, these two sides are equal, right? These two sides are equal. We call these triangles, where at least two sides are equal, isosceles triangles. So in isosceles triangles, we have two sides that are the same. In geometry, In order to show that things are the same, we put a line through them. So here, for example, by putting these two lines through these two sides, I am showing you that this side is the same, it's equal to this side. Now they might not be in reality, like if you take a ruler, because I made them by hand, they might actually not be. But if the problem is giving you this, where you have these two sides and they have lines through them, then you should consider them equal. And again here, the same. These two sides are the same, so I'm going to put lines through them to show that they are the same. These two sides are equal. But what if instead of having a triangle that only has two sides as the same, I have a triangle that has all three of its sides being equal? So something along, and these are actually very, very difficult to make because you have to be really specific. So this might actually not be, but you could say that, that's pretty close actually. So if you look at these sides, they look like they're all pretty much equal. They look like they're all about the same. Maybe because I drew them by hand, they're not, but they look pretty close. So let's imagine that they are. So in this case, we said all three sides are equal. If all three sides of a triangle are equal, then we call that triangle equilateral. We call these triangles equilateral. So again, scalene triangles, no sides are the same. In isosceles triangles, two sides are the same. And in equilateral triangles, all sides are the same. A fun fact about isosceles triangles and about equilateral triangles, we'll talk about them later. A fun fact about isosceles triangles is that apart from having two sides that are the same, they also need to have two angles that are the same. So specifically these two angles right here. The angles that are created by the side that is not equal with the other two. These two angles need to be equal in an isosceles triangle. So you'll see that this will be equal with this in any isosceles triangle you make. And in an equilateral triangle, what you will see is that all three angles are actually 60 degrees. Always. All three of them need to be 60 degrees. So apart from having two sides being the same, isosceles triangles also have the two angles created by the unequal side are equal. Let's put some periods here because we haven't put them. Let's make this a little smaller. It's too big. You should also be copying these because they'll be very useful in your exercises. The exercises that you have on Wednesday and Thursday. And we said that in an equilateral triangle, all angles are equal to 60 degrees. The scalene, because they have nothing special about them, it's not that we can use anything to define them, basically, because by definition, their sides are not the same, means we really don't know anything about them. Since none of them are the same, all we know about them is that their angles, the sum of their angles needs to be 180 degrees. Other than that, we really don't know anything about anything specific. We can't say anything specific about the scalene triangles like we can say about these. Okay, so before we move on, I want to write these definitions in Greek as well, just so that you know the terminology. Just the titles, basically, of each triangle. In Greek, scalene is scalino. Wait, why isn't it writing? Sorry about that. Let's try that again. Scalene is scalino. And they do sound the same, so you can, if you remember one, you can remember the other. And the same goes for here. This is a Greek word, as you can imagine. Isosceles is isosceles. The last one has a bit of a different name. Equilateral triangles are called isoplevra. Meaning that they have equal sides. All their sides are equal. Okay, so that'll be all about the types of triangles based on their sides. I will be deleting all of this now so that we can move on to the height of a triangle. So if you haven't copied any of it, you really should. It's going to come in handy. Actually, let's just hide it. So next up, we're going to talk about the height of a triangle. Now, what do we mean when we say by that? What do we mean when we say the height of any shape? Well, if you imagine that we made a triangle and we put it on the floor somewhere, and we asked how tall is this triangle? What would we do? We would take out a measuring tape and we would just measure how tall it was, like we would with a person or any object really that we want to measure its height. Okay, but how? Let's say I had this triangle, right? And I put it on the floor. So I said, how tall is this triangle? What is the height of this triangle? What is its tallest point? That would be this point right here. I would go and I would measure the distance from that point to the ground. Okay, great. But what if instead of being like this triangle was a little different? What if it was shaped like, what if, not shaped basically, what if it was turned like this? And I still wanted to find its height. Well, I sort of imagine, well, what would happen if the ground also switched and went like this here? And if the ground, and you can tilt your head to the left a little bit to imagine. Then again, I would measure the same thing, the distance from this point to the ground. Or you can imagine, if you want to, that I just turned it back this way, and, well, what's the distance to the ground? What, though, would happen if I were to rotate it like this? Well, now it sits on the ground like this. So I'm not going to put the ground here necessarily. It depends really what point I want to find the height from. So do I want to find the height from this point, or from this point? It really depends on what the problem is asking from you. Before we continue, we need to talk about how we find the distance of a point from a line. So I'm going to make one, two, 3 points. Let's say we want to find the distance from each of these points to this line. Well, okay. We can say how far is it to get from here to here? Yes, of course. But which point on the line do you want to get from here to here, 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 or here? Because all of these distances are different. This is different than this, than this, and than this. So which one of these do you want? Which point? And considering that the line has infinite points, which one of all of these do we really want? The answer is we need to find which of these lines is perpendicular to this line. We need to make a line that is perpendicular to this line in order to say, okay, that's the distance from this point to this line. It can't be this or this or this or this. It needs to be the one that is and there can only be one that is perpendicular to this line. So what we would do is we would take a ruler and we would place it on the line in such a way that we could make a perpendicular line to this line, but one that meets this point. So let's actually do that. I am now going to take this ruler, I'm going to turn it on its side in such a way that one of its lines is aligned with my current line. So it seems like this is pretty much aligned. So if I had it like this, that would be a mistake. I can't make a perpendicular line like that. If I had it like this, that would also be a mistake. I need to have it in such a way all the lines on this ruler, see how they're aligned now with this line? See how they're on the same line? That's what I want to make a perpendicular line. And I'm going to place it at a certain point where, oh, you see how it's nearly touching that point that we care about? Right there. And then I'm going to draw the line. There we go. And then for the next point, I'm going to do the same. So right here. But what about the next point? The next point, as you can see, no matter how close I try to get, it's not going to cross this line because this line ends here. Well, what I do in this case, where the line ends, is I imagine what would happen if I were to extend it. I can actually use my ruler, can turn my ruler on its side again in order to make this line, in order to imagine where this line would go if it continued. Where would this line go if it continued? Say here, here, here. You see how I'm not making connected lines and I'm just making partial lines? It's because this isn't really part of the line. We saw what the line is. This is where it would go if it continued. Does not. But if it did, this is where it would go. And now I can take my ruler again. I can turn it back to make it again perpendicular to the line that we had before. So like this. Yep, there we go. And we can find where exactly we would need to place it in order to touch the point. See now how it's touching the point right there? And we would draw this line right here from the point until the imaginary part of that line. And that line that we just made is the distance from the point to this line. And you might be thinking, okay, but what good is any of this? What does this have to do with what we were talking about before, the height of a triangle? Well, you see, this is exactly how we find the height of a triangle. So let's make a triangle. Let's make this. And I'm just making random sides. I'm not making anything in particular. If I want to find the height, it depends, as we said before, which point I want to find the height from. So let's actually put these together. Let's say I want to find the height of the triangle from this point up here. In order to do that, I need to use my ruler to bring a line that is perpendicular to the side that is opposite of this point that this point is looking on, and that will be the height of the triangle. So what's the side that I want? The side basically that isn't touching this point. So that would be this side. I need to bring a perpendicular line to this side. So I'm going to take my ruler, bring it here, and then draw my line. And this line that I just made is the height of the triangle from this point. Then I'm going to find the height from this point, just because why not? Basically, I imagine that the side that the point is looking at, the side that is not touching it, that is not touching this point, I imagine that side is the ground. So here we imagine that this was the ground, which is quite easy, but now I have to imagine that this side is the ground, because that's the side that is not touching this point. So again, I need to bring my ruler and make a line that is going to be perpendicular to this line and touch this point, cross this point. So I'm going to turn my ruler to align it with that side that I care about. There we go. And then I'm going to make the ruler touch the point. There we go. And now I'm going to bring this line. And that's the height from that point. Okay, great. But what if I give you an obtuse triangle like this? Here, and I ask you to find the height from here. Now, you might already be thinking, well, how am I going to draw a perpendicular line from here to here? And this is where that technique that we talked about before comes in, where we say, okay, I'm going to place the ruler on this line and project this line and imagine where it would go if it continued. And then I'm going to bring the perpendicular down to the imaginary part. So let's do that. I'm going to place my ruler directly on this line. And it has to be completely aligned with the line that I care about. Okay, here we go. And then I'm going to continue this line. So where would it go if it continued? Just like we did before. This process would be a lot more exact with pencil and paper. So here you can see where this line would go if it continued, where it is projected. Okay, great. And now I can turn my ruler to make it perpendicular to the line, like so, and I can bring it to the point. And I can bring this line down right here. And this line that I just made, right? This line that I just made, that is the height of the triangle from that point. Right there, that's the height of the triangle. So imagine this was the ground, right here, this line is the ground, right? And we're measuring how tall the triangle is. We would get the measuring tape, this is its tallest point, that's how tall it is, right? Okay. Now, where we use the height of the triangle, that's a completely different story. It's not necessary to talk about that right now. Right now, all we need to know is what the height of a triangle is and how we draw it. So, I will see you guys again tomorrow. Have a good day.